Hello students. So today we will continue the same module 6. So let's start. So first of all we have to understand relationship of angular parameters with linear parameters. Already we have discussed in the previous session, right? But today we will see the vector form. Okay, so let us say the particle is going in circular motion. Here I am only considering circular motion, right? And let us take its instantaneous motion along the circle. So this is like a small arc length, and this small arc length is just like a small linear displacement, dl. You may write it as dl vector as well. And this is the radius r, and this is small angular displacement d theta that is happening. So d theta is equal to dl by r. All of us know this. This is the angle in radian is equal to arc length by radius. Now when you bring it this side, you may write dl is equal to d theta into r, but in terms of vectors you can write it like this. dl vector is equal to d theta vector cross r vector. Now you may wonder whether d theta or the small angular displacement is a vector quantity or not. Yes, it is vector. It is vector. Okay, but it is not expressed in most of the problems. Why? Because it's like a linear, like in linear motion, either it can be towards right or left, so plus minus sign is sufficient, but actually it's a vector quantity. So angular displacement, angular position, angular velocity, angular acceleration, all these are vector quantities, right? You may say that it is like a rotational vector. That's a different thing. You may give it a different name, but it is a vector. Okay, dl vector is d theta cross r. Now then velocity is just differentiate dl by dt. When you differentiate this dl by, that means dl by, just divide by dt, right? So dl by dt will become velocity, and remember this velocity is the instantaneous velocity. It's the velocity at this point, right? Which is equal to omega r that we write. So this is omega vector cross r vector. And when you differentiate this instantaneous velocity, which is tangential, you will get tangential acceleration, which is alpha cross r vector. Alpha cross r vector, right? And what is centripetal acceleration? Centripetal acceleration is omega cross v. We know the formula, it is omega square r or v square by r. But in terms of vector, how to write this? Because sometimes they will ask as a vector, so cross product you have to do, right? In terms of I, j, k, you have to calculate. So omega cross v vector. Next that we have to understand is relation, and now this is a very important thing, because in textbooks they don't mention it completely. This concept you have to understand. Relation between v vector and omega vector. In general, let us say body is not going in a circular path. It may go in a different path, right? It may go in a different path. It does not matter. Still we can try to find out what is omega vector. It may not be going in a, it may be going in a straight line path, but still instantaneously we can calculate angular velocity, right? We can calculate that. So let us say, for example, here the body is there and its velocity is v vector, and this is of course radius vector or position vector of the body. And about this origin you want to calculate omega vector. So this v vector we can resolve, one is perpendicular component. Perpendicular to what? Perpendicular to the position vector or radius vector, and parallel means parallel to the radius vector, right? So we know this v equal to omega r, that this formula we apply in case of circular motion. So if you consider the perpendicular part, that is like a tangent to the circle, right? Tangent to the circle. So v equal to omega we can apply only for the perpendicular component of velocity, not for the v vector or v. This is what we have to note. V perpendicular is equal to omega r. Omega is equal to v perpendicular by r. Now I want to write the omega vector. So omega vector will be magnitude and unit vector. Magnitude and unit vector. Now magnitude already I told, v perpendicular by r. Now what is unit vector? Now unit vector in the direction of omega cap, that is omega, if you consider here the body is going anti-clockwise, so omega vector is coming out, right? Omega vector is coming out. Right hand thumb rule also says that when you curl your fingers, right hand fingers, in anti-clockwise direction, the thumb is coming outward, right? So that we can also say as r vector cross v vector. Take that vector and divide by its magnitude. That's the unit vector. So unit vector can be calculated if you know the vector, and we know a vector which is perpendicular to r and v, or it is parallel to omega. So r cross v by magnitude of r cross v. So when you see that v perpendicular is nothing but v sin theta. Of course, theta is the angle between r and v vector. Okay. So this is r cross v, and r cross v magnitude is r v sin theta. Here you see v sin theta get cancelled. Omega vector is equal to r cross v vector divided by r square. Here r is not the radius of the circular path, but it is just the position vector about which you want to calculate omega. This you have to understand, right? This omega vector is calculated in this manner. Why are we learning vector? Because they will ask questions in terms of vector. The problem with the vector is that magnitude you may calculate from here itself, but direction you need to calculate unit vectors. Okay. Otherwise, you can use this direct formula. Omega vector is equal to r vector cross v vector by r square. Right. These are some of the critical things. Then let us move next. So next we should try to understand two important terms. One is RPM, and another is RPS. So RPM is revolution per minute, and RPS is revolution per second. Okay. And here you need to note that these are nothing but this RPM, RPS is nothing but it is frequency. It is frequency. What is frequency? So let's understand frequency. Frequency, if I denote by symbol F, it is equal to number of revolution per second, or the rate of number of revolution dn by dt. This is what is called frequency. Here n refers to number of revolution. N refers to number of revolution. Okay, let us say that a body is going in circular motion. We are considering the circular motion, and let's say it has revolved n number of revolutions. So the angle that it will be rotating, angular displacement theta, is equal to n into 2 pi, because you know in one revolution it goes 2 pi, n revolutions, right? In one revolution it gives 2 pi angle, n revolution it will get n into 2 pi, right? That's the angle it is rotating. Now if you differentiate to calculate omega, d theta by dt you can do. So 2 pi each constant comes out, dn by dt, which is nothing but frequency. So that's why the angular speed omega is 2 pi into frequency. Okay, right? So this is the general definition: RPM, RPS, frequency, and angular speed. These are different terms. We have to understand this. There are slightly different meaning, because angular speed omega is rotational speed. Frequency is based on number of revolutions. Okay, now RPM, RPS are the units of frequency. So let us consider now different type of rotational motion. So in rotational motion, there are two types: uniform rotational motion, right, and non-uniform. So let's discuss uniform rotational motion, which is part of uniform circular motion. So in uniform circular motion, that speed is going to be constant. This is the speed, or angular speed omega will be constant, right? Angular speed constant. So there is no angular acceleration d omega by dt. This is going to be 0. Tangential acceleration, which is rate of change of speed, or which is r into alpha, this is also going to be 0, right? All these things will be there. And also we can note that we can define there is a time period for that, or frequency. Frequency will be 1 by time period. 1 is the number of revolutions, so if there is a 1 revolution, the time taken is called time period. Okay, and this should be defined only in uniform circular motion or uniform rotational motion. Rotational motion. Frequency can be defined in any type of motion, but time period is defined only in uniform circular motion. Why? Because it is taking equal time, right? Isn't it? So F equal to 1 by t is only for uniform rotational motion. Okay, and here the only equation that you are going to use, the equation of motion you say, right? The equation of motion, just like in the linear, motion speed is equal to distance by time. Same way here, the only equation is speed, is angular speed, is displacement. If you take theta as the displacement in time t, that's what we are going to use. Or you can say displacement is angular speed into time, right? And you can also say time is equal to displacement by speed, right? So that's the only equation you are going to use in uniform rotational motion or uniform circular motion, right? Omega is going to be constant, so that's why you can write it like this. What about the non-uniform circular motion? Non-uniform rotational motion. Non-uniform rotational motion. So the first thing that you should know about non-uniform rotational motion is that there is an angular acceleration alpha, and here we can consider two cases, right? One you can consider is uniformly angular accelerated, uniformly angular accelerated rotational motion. So uniformly angular accelerated rotational motion means alpha is going to be constant. Alpha is constant, and if you see the tangential magnitude, of course, of tangential acceleration is r into alpha, that is also going to be constant magnitude. Of course, the tangential acceleration keep on changing direction, but magnitude will be constant. Or you can say the centrifugal acceleration, which is omega square r or p square by r. This is also going to be constant in magnitude, of course. Magnitude, right? Direction is changing. Okay, then here you need to note also the equations of motion. So for example, let us say if a body is going to rotate in a circular motion, initially its angular velocity is omega naught, and let's say it has rotated for some angular displacement, right? Radius is r. It has rotated by an angle of theta. Now the angular speed is omega, and linear speed also we can write, but no need, we'll just consider angular motion. Just now you have studied v equal to u plus at. Same way the final velocity is omega, initial velocity omega naught plus alpha into t. T is the time taken or time interval. Initial time is 0, here time equal to t. Okay, so we can apply this equation 1. Remember these equations in linear motion, we have already done that. Similarly, displacement theta is equal to ut plus half t square t plus half alpha t squared. Then third case, v square equal to u square plus 2s omega naught square is omega square plus 2 alpha into theta. Similarly, the average velocity, average angular velocity is initial plus final by 2. And also the displacement, angular displacement in nth second, theta n is equal to, just like u plus a by 2, right? 2n minus 1. So u means omega naught, u plus a by 2, a means alpha by 2, 2n minus 1. This is what it is. So all those formula for linear motion can be applied here as well, right? We can apply those equations. Only thing is that the symbol has changed because it is now rotational motion, right? Okay, so this is rotational kinematics. We have completed rotational kinematics. Then we'll go next lesson into rotational dynamics, right? Thank you for your attention.